So Masoumeh, she will talk about modes of posterior measure for Bayesian inverse problems with a class of non-Gaussian priors. So we're very much looking forward to
Thank you very much, Nadia. So what I'm going to talk about today is based on joint work with Sergius Agapio in how does this work? Oh, I found it. In Cyprus, Martin Berger in Munster, and Tapio Helin in Helsinki. Okay, so what I'm interested in is the modes of a probability measure mu. So what I know about this probability measure is its rather Nikodym derivative with respect to a reference measure, which I know as well. So mu naught and f are given, and I'm interested in modes of mu. Now, mu is a probability measure on a function space, okay, rather than a finite dimensional space. So if I had a finite dimensional space and I had Lebesgue density, then I could have calculate the density of measure mu in terms of this reference measure and f, and then the modes of mu would be just the maximizers of this density. When I am on a function space, then I don't have a Lebesgue density, and what I'm asking is how I can define and characterize these modes. Now, in context of the Bayesian inverse problems, or Bayesian approach, this mu naught, as we have seen repeatedly in previous days, is the prior measure, and my mu is posterior and f the likelihood, proportional to the likelihood. Now, in that context, modes are called maximum of posterior estimators, so I will use the terminology interchangeably. Okay. So I'm going to define two notions of modes. We can strong map estimates or modes of my measure, and what I'm interested in is a class of non-smooth priors called best of priors. So I will discuss those, and then I will also discuss some weak posterior consistency results. Okay, so my setting is where X is a function space, infinite dimensional space, so I'm going to consider it a separable Banach space. And then the way that I define modes is topological, through a topological way. So what I do, I say I look at small balls, while the probability of small balls while I'm moving them in my space X. So I fix the radius of this ball, I move it in the space, I find the center which gives me maximum probability, and then I look what happens to these centers when delta, the radius of the ball, goes to 0. Okay. So based on this topological idea, this is a formal definition, a more general one. So I have got rid of these intermediate z deltas. So I have for each fixed delta the maximal probability of these small balls of radius delta, and then what I call map estimator is the points z tilde which satisfy this limit. No, it's based on, if you can define this intermediate z delta, then you will get this, if you have the limit in a good sense. Okay, so this is the definition. Right, now we don't have the density in infinite dimensional space, and we are interested in moving the balls, and then the closest that we can get to this density is when we move the balls over the space of admissible shifts, okay, of this measure. So what I mean is this. So remember from definition that we are interested in asymptotics of this ratio, okay? So if I can find a subspace of my original space X where this ratio exists pointwise, okay, then this is the closest thing I can get to the density, definition of a density. So Z1 and Z2 are not in X, but in a much smoother space, which is subset of X. And for this, then this limit is defined, okay. Suppose that I have that situation, that this limit is defined, then the log of this limit gives me a functional I, which I call Onsager-Machlup functional. Okay, this is the heading of this frame. Right. So, for example, if you have a Gaussian measure with covariance operator C0, then you can show using the Cameron-Martin theorem that the Onsager-Machlup functional is the norm of U in Cameron-Martin space to the power of 2, and this space F is just the image when X is a Hilbert space, is the image of X under C0 to the power of half. And then for such a Gaussian measure, you know that the covariance operator is the smoothing, so this F is smoother than the original X, is smaller than original X. Okay, so now what we are asking is this: do minimizers of I characterize the modes of mu in the sense that I defined it before, in that topological sense, right? And then the answer is non-trivial because the modes are limits of sequences in X, which is a bigger space, while this Onsager-Machlup functional is defined over subspace of this XF. And for example, in the case of the Gaussian measure, the measure of F is 0 actually on the Gaussian measure, right? So it's a smaller, much smaller space. So that is what makes it non-trivial. Okay, so recall what I'm interested in, which is the situation that I know the Radon-Nikodym derivative of measure mu with respect to a reference measure, and it's given to me in form of a function of u, which, since I'm talking about probability measures, I'm going to express it like exponential of another function. Okay? And then I know mu naught. Now, in the situation that mu naught is Gaussian, and this right-hand side is locally Lipschitz, we know the answer to this question. So yes, it can be characterized by minimizers of the Onsager-Machlup functional corresponding to measure mu. Okay? So it's good to notice that this is, although it's non-trivial to show, but it's not surprising, because if you are in the context of finite dimensions and mu naught has the density e to the power of some function of u, no, if you are in finite dimension, then mu would have the density e to the minus phi of u minus w of u. So you are just minimizing to find modes of mu, you are just minimizing this function. Right. Now, of course, one is interested in knowing the answer for more general priors, and then the way that we have defined it, and with those topological definition over the whole space X, and with the difficulty that I explained, that the definition contains limits of sequences in the bigger space, and this Onsager-Machlup functional is defined in a much smaller space, it makes it difficult to apply to general situations. And for that reason, Tapio, Helen, and Martin Berger gave this weaker notion of modes, which is easier to generalize, okay, for a more general reference measure I'm going to explain in a minute. And what they say is that, okay, so instead of moving those little balls, shift them, okay, with shifts living in that bigger space X, let's shift them in a smaller, much smoother space, okay? So they say, so these are the proportion of the balls that we are looking at, the original ball with center U hat, and then the shifted ball, and then we say that now suppose that this shift is in a very smooth space, okay? And then if this limit is less than or equal 1, then you're going to have, for a fixed U hat, then U hat is a weak map estimate. That's their definition. And then since this is dependent on that E, that subspace that you are shifting over, you can call it a E weak mode, right? Depending on that space. And then with this definition, they showed that for a smooth enough convex measures, convex priors, the modes of the posterior are characterized by minimizers of the Onsager-Machlup functional. Then very recently, Tim Sullivan and Han Lee showed for non-atomic Borel probability measures on the X with the same properties that we have here, that weak and strong modes coincide. So putting these together, you also have the result for the strong modes for smooth enough measures, right? So I'm going to tell you a little bit why they need this differentiability, and then I will go to the case that I have a non-smooth measure. Yeah.
So what does it mean that they coincide if the weak mode still depends on E? For every dense subset, the weak mode coincides with the strong mode, or for some dense subset, or?
For any dense subset of X, the result that Han Lee and Tim Sullivan have is for any dense subset, yes. Mm-hmm.
The strong mode is unique, isn't it? So, I know, so for a Gaussian measure, for instance, the strong mode would be unique.
That's right, but note that H is the space of shifts, no? So you have U hat itself might be in a weaker space, no? But you are shifting it in a smoother space. Yeah? No. Okay, right. So how do we define the differentiability in this context? So you have a measure on an infinite dimensional space, and therefore you cannot have differentiability in all directions in that space, because the space of admissible shifts are also only in some directions. So you need to first define differentiability along certain directions. So how do you define differentiability? So for any Borel set, you shift it along this direction, and then you are basically differentiating with respect to t, this parameter, real parameter t, right? And then all the directions over which you can define this limit, you call the space of differentiability. Now, if you have a standard Gaussian measure, then you can easily write the measure of a set A plus the change in this direction like this, no, after a change of coordinates. And then calculating this is just differentiating the integrand with respect to time. No? And then as soon as you do that, you get this HU out here. And then similarly, using the definition, you can do that over a function space X, and you get a very similar expression here for an infinite dimensional measure, Gaussian measure. Okay, using the definition. Now, this thing you can look at the gray thing as the Radon-Nikodym derivative of this derivative of measure with respect to itself. Okay? So let me give that a name. So I call it logarithmic derivative. It is called logarithmic derivative of mu, which is the derivative of this derivative with respect to itself. No, the Radon-Nikodym derivative, the gray stuff. Okay? Now, if you think about it, if you go again to the finite dimensional setup and think about it here, so if you calculate the logarithm and you differentiate, that logarithmic derivative in the finite dimensional setting is like the derivative of this guy with respect to u. So if you want to calculate the minimizer, you want to have the derivative of this to be 0. Okay? So in this context, this translates to having the logarithmic derivative to be 0, right? And that is what they need. They want the 0 points. They look at the 0 points and they show that they coincide with the weak modes, right? And then they can show that the 0 point of this logarithmic derivative are also the minimizer of Onsager-Machlup function. Okay. Right. So what they need, they want mu to be convex, and of course, since they are looking at the 0 point, they want eta h to be continuous. Okay. They want it to have a continuous representative, since we are talking about a function over a function space. Now, we are interested in Besov priors, and what are these? We are going to define them through Karun and Loew expansion of their draws. So Chris Schwab gave this nice explanation of uncertainty parametrization in his talk. So we are talking about that basically here. So we have a basis in our space, an orthonormal basis, and then you say that any draw you can write in terms of this basis as a random series. So the coefficients are random though. So this side j are the orthonormal basis, non-random functions, and then the coefficients are random. Okay, now this coefficients alpha j then define how smooth the draw is, the draw u is. So in the case of the Gaussian, the familiar case, psi j, in all direction you have a Gaussian measure, and then psi j is an orthonormal basis, any orthonormal basis in L2. And the Besov one is just a generalization of that. So in the each direction in your orthonormal basis, you have an exponential measure, and then this psi j are orthonormal wavelet basis. And then alpha j are chosen in a way that you get in your calculation Besov spaces out as the spaces of admissible shifts of the measure. Okay? But in essence, they are just the measures which are exponential in each direction of your basis. Now, so you see, in each direction I have exponential of minus absolute value of x to the power q. I am interested to the case where q equals 1. Okay, that's the case that I'm interested in. So I have double exponential measure in each direction. And then alpha j is not very important. It's just chosen in a way that the space of admissible shift is a certain Besov space. Okay, so why I'm interested in these? Because they promote a sparsity, and they are therefore useful when we are interested in finding a function which has a blocky structure, right? Continuous with few irregularities. Now the problem with this is that that logarithmic derivative that I just explained is not smooth, no? So you have, you see, the log of this, if you look at each direction, is just the absolute value function, and it has a discontinuity at 0. The derivative has a discontinuity at 0. So it's not continuous. Now, if you remember the definition of the E-weak modes, so a U hat in X is an E-weak mode if this proportion under shifts H in this smoother space E is less than or equal 1, the asymptotics of it. Now, the numerator here, I can just write it as the measure of the same ball in the denominator under the shifted measure along edge, right? So, and then noticing just this, you can show that if you can find a smooth enough space over which the Radon-Nikodym derivative of the shifted measure is continuous, then this limit over X equals the Radon-Nikodym derivative pointwise. Okay? And then it turns out that continuity of the Radon-Nikodym derivative is then enough to show the equivalence of weak modes and the minimizer of the Onsager-Machlup function. Okay. So that is what I'm going to use. So let's see what we have about the best of measures, the best of measure that I'm interested in, the exponential one. So I can calculate the Radon-Nikodym derivative. It's a product measure over R infinity, so it's not difficult to calculate its Radon-Nikodym derivative like this. And then you can show that for smooth enough spaces H, okay, so this variable R is a measure of a smoothness, so the bigger it is, the more differentiable the function is. So for R bigger than S, you have the Radon-Nikodym derivative continuous for any t less than S minus d, and d is the dimension of the space. Okay. So notice that this alpha j relates to the exponent S. So for each u in bt1, this guy here, the sum of these guys is infinite. Now what we are saying is that if if H is smooth enough so that these guys decay fast enough, then the sum of these two would cancel out, and you would get what you need. You would get the continuity. Okay. So as soon as we have that, then we can also find the Onsager-Machlup functionals. Okay. The space over which we can define it is BS1. So you can see that the E is smoother than the space of admissible shifts as well. Okay, the one that we define the weak mode through. And then putting all of these together with continuity of the Radon-Nikodym derivative, we conclude the characterization for this Onsager-Machlup functional for mu. No? So compare this with this thing that I had written on the board. Okay, so this is what we have, that indeed the weak modes and therefore the strong mode, by the result of Lee and Sullivan, are characterized by minimizers of I. Okay, now the structure that we have for this best of measures, we can also show for each fixed delta the existence of a center which maximizes the probability and the convergence in an appropriate sense as well. Okay, so that's an extra thing, but the important thing is this one. Okay, now having this, I'm going to tell you a little bit about this weak posterior consistency results. So we are in the situation of the Bayesian inverse problem. We have a true we have an underlying truth, okay, that we want to find, and I'm calling it U dagger. G is locally Lipschitz, as I needed also, if you noticed in the previous result, to hold for this characterization, I need my phi, which is defined through that G to be locally Lipschitz, so I assume the same thing here. And then I am in the situation that I'm collecting data, and I can do that as much as I like. So, and I would like to know, as I am tending n to infinity, what happens to the mode of the posterior that I get through the Bayesian approach. Okay? So if I apply the Bayesian approach to this problem, I get this relation for the posterior measure for n data. Now, by the result that I showed you for a Besov prior, the modes are the minimizer of this functional. Okay? And I want to know what happens when I tend n to infinity. Right? So if my truths live in the space of admissible, no, this is actually a little bit smaller than the space of admissible shift. This is the space over which the Onsager-Machlup functional is defined. If I have the truths in there, then I can show that G of UN, G relates to my forward model, converges in probability to G of truths, right? So for a general G, I can not hope to say much more than this. If G is injective, I can show the convergence of UN to the truths in my space X in probability. Or if I restrict myself to a subspace of X over which G is injective, I can again say that. But otherwise, what I can say is only that a subsequence of this UN converges to truth in probability. Okay? Not to the truth, actually. To some US star, this should be US star, sorry, for which G of US star equals G of U dagger. No, because I might have many US star for which G of US star equals G of U dagger. Okay. Right. And just some concluding remarks that, of course, this was a weak posterior consistency result. What you are interested in ideally is the contraction rates around this mode as you are collecting more and more data. We have this for direct problems with a Besov prior B, S, Q for any Q bigger than equal 1. And using this methodology which Gosal and van der Waart have devised, and also van der Waart and Van Zanten for the Gaussian priors. And then when you have this, it seems that then you can also go to linear inverse problems if you restrict somehow to subspaces over which you have injectivity, as we also saw in that weak posterior consistency result. And also I would like to mention these local modes. So the same definition that we had for the modes, if you restrict to subsets of X through which you can define local modes, weak and strong. And then all I said during the talk was about convex priors. There are non-convex priors which are locally convex, like Cauchy, and then maybe these local maps can be useful to get similar results for those. That's it. Thank you.
question, but in these settings, when you have exponential priors, just studying the MAP might be not very informative in terms of the uncertainty quantification and the whole posterior distribution. So if you take a standard linear model and you take a Laplace prior, then you can show that the MAP estimate is the lasso. So you would think you promote sparsity, but the actual posterior distribution itself is far from consistent and the contraction rate is very bad. So I'm a bit surprised actually for the priors that you using here. Do you really expect to obtain the optimal contraction rate? I mean, so it might be that the MAP estimate is very good, but that the posterior is actually way too much spread out over the parameter space, over the space of balls. So what you have on this last slide, you really believe that you get the optimal rate with these priors?
Here.
No, I mean, there's no rate. I mean, that's just consistency for the MAP estimate. What I'm saying is that I think that the MAP estimate might be a good estimate, but the posterior distribution as a whole might be very bad.
Yes, right. So what we have, so I am not sure if they are optimal or not, but what we have is something like that. So if you have so this is the context of van der Waart and collaborators. Now we can show something like this, right? With T, the worst, which is the worst T is for B S1, and this T somehow depends on this S. I'm not sure if that's optimal or not. And then I'm not sure if lasso it is exactly the same as what we are considering
it's not
here.
Exactly the same, but
Yes.
it is related to the L1 type penalty, and the priors whose MAP sort of mimic nice lasso type estimators usually are nice on the level of studying the MAP estimate, but it is conceivable that the posterior is very bad. And for the lasso, this is precisely what happens, and you can prove this. And your setting actually looks a bit like this. So I would be quite surprised if the posterior corresponding to this exponential prior produces optimal contraction rates. I think that, you know, maybe if you get suboptimal rates there, you shouldn't try to prove anything better.
Right, yeah, okay. Yes.
Right, so a prior is going to encode the person who's doing the data analysis, their prior belief on some parameter.
Mm-hmm.
So can you give me some, is it obvious to people who are solving this sort of problem that you're aiming at on how to set up a prior to encode their own belief of what the parameter looks like before they start the analysis?
Right. So the only thing I can say is that so we are looking at this best of priors, and the reason that we are looking at them is because in some situations you have an unknown that you know that it is continuous almost everywhere with few irregularities. For example, in this subground flow, where you are interested in the permeability of rock, let's say. K gradient of P equals 0. And then you know that permeability is piecewise smooth, so you would like to consider that, to take that into account, and such an L1 type best of prior works for that. But yeah, apart from that, I'm not sure if I can say anything else.
Okay, thanks.
Yeah.
Just a quick idea. I mean, there's quite a lot of stuff on contraction in the context of stochastic dominance. So I wondered if, as you move forward, as you assimilate the data, you get a more general type of contraction rather than just say it's like L1 or L2 contraction. Is there some general stochastic dominance principle which might be discovered during this wonderful theory. That you get more and more peaked, the posterior can be more and more peaked in some general sense.
Right. So I am not sure if I understood your question. You are saying that instead of considering L2 or LP,
You consider a general stochastic ordering something to do with the peakness of the distribution, as opposed to a particular order preserving function like L1, L2, or something. Just an idea.
right? So this contraction rate results, they show that how quickly you get concentrated inside a ball around the truth.
Yeah, but that being concentrated inside the ball is a kind of peakness.
That's right.
And maybe you could develop it into a general peakness criterion. If you like,
Right.
as you get balls bigger and bigger,
You have to be careful because in these general situations, if you don't have a Gaussian prior, it might be that the posterior contracts around the true point, but the MAP is actually outside of that ball. The maximum doesn't have to be where the mass of the posterior sits. In a Gaussian setting, of course, the mean and the maximum are the same. So actually, your contraction rate wouldn't tell you anything about the performance of the MAP. So I don't think one can answer your question in this setting.
Sorry, why is that?
Well, you can have a distribution that has a maximum, but most of its mass is somewhere else. Unless it's Gaussian and symmetric. I mean, you don't have any formal conjugacy in your model, so you have some. I mean, I don't know what these convexity assumptions you have precisely imply, but I'm sure the posterior is not unimodal.
No, that's right. It's not unimodal. Yeah.
So
Yeah, but that's right. The posterior is not unimodal, and what I was telling about this contraction rates is only about the direct problem. So you know that you only have one mode with the one that I was telling you.
yeah, but once you go back in the inverse problem,
That's
you lose
true,
this,
absolutely.
it could be that the MAP is somewhere far out, and the posterior sits somewhere completely different. So I think it's very dangerous in inverse problems to study only the MAP.
Yes. Yeah, I agree with that.
Just to temper, Richard's exactly right, but the problem is it's the regularizer. So the lasso regularizer leads to non-Bayesian procedures because of the disparity between the mode and the posterior. But there are other regularizers which are more stable, which you can get the posterior contraction.
Right.
So they have to have heavier tails, and or some combination of therewith.
Yeah.
So the issue for you, I think, is the Besov prior more like the L1 or these other
Yeah.
kinds of things.
So is that the reason that you were considering this uniform coefficients?
I mean, bounded coefficients are always easier, but yeah, so they I mean, this doesn't. I mean, maybe we should take this offline because people want to have coffee. But
Yeah.
Okay, so thank you very much once again.